Well, good afternoon, everybody. Welcome to the Stats for the Masses webinar, Power Analysis, a Brief Yet Useful Overview. I'm so glad many of you could attend today. My name's Elaine Eisenbeisz. I'm the owner and principal statistician here at Omega Statistics. We've had quite a large number of registrants this presentation, so I see many are attending with us live. So thanks for taking the time to join us live, and I'll do my best to make this run as smoothly as possible. So today I'll present an overview of a priori power analysis. A priori techniques are used when you're designing a study at the very beginning of it in order to determine your best sample size. Today's just an overview, but I hope that the information you receive today will give you some ideas and guidance on designing your own studies. As I say in all of our all the webinars we have, use what you learned today, apply it in a holistic way. Power analysis is part of the big picture of a study's design. Even though it's a little piece in the big picture, it's really useful. The presentation should last about 30 or 40 minutes, and then we'll take some time at the end to answer some questions from the audience. I've currently muted the line so that only my voice can be heard, but my assistant is here with me, Heather Crutcher, and she's monitoring the chat board. So feel free to type any questions you have on the chat board, and Heather will choose some to ask me at the end of the presentation. Also, if you have any problems, technical problems, maybe type it on the chat board. She'll try her best to solve it as I'm talking away. If you have technical issues and you just can't seem to talk to anybody or figure it out, reboot. You can just log off, log back on. Sometimes that solves everything. So let's go ahead and see if I can bring up our slide. Okay, so before we begin, I'd like to take a minute to tell you about Omega Statistics and our Stats for the Masses webinars, newsletters, workshops. Statistics can be difficult. Even for seasoned researchers. Often textbooks, classes, training programs, they make things a little more confusing. Just throw more difficult words into the mix and such. My goal with the Stats for the Masses series is, and for Omega Statistics actually as a company, is to inform and educate about statistical concepts and try to do it in the most layman's terms possible. Sometimes that's not easy. We try to do our best so that everyone can see the elegance and usefulness of statistics. We do have another webinar that will be coming up. It's scheduled for January 22nd, so next year already. It's tentatively entitled GIGO, No-Nos, Problems and Solutions of Data Preparation. So sometimes, GIGO is garbage in, garbage out. So we want to make sure that we're cleaning our data correctly and putting it into the analysis correctly so we get the results that are valid. So the webinars are always free, and they are recorded, so if you can't make it to a live meeting, you can always review it later. Or you can do both. You can come live and then review it all you want afterwards. So let's go on and tell you a little bit about Omega Statistics. We're a private practice statistical consultancy. We are in Southern California. We do medical and clinical research, clinical trials phases 1 through 4. We do design and analysis of experiments. We are involved in epidemiological studies. We work with large data. We help researchers with their journal articles. We usually will run the results and do a reporting for them. We also assist with exploratory design and predictive modeling. That's probably some of the most fun things that I think that we do, building models, trying to figure out what might be important. We do help with dissertation assistance. We help with the methods and the results chapters. Those are usually chapters 3 and 4, and that's usually whenever a PhD student starts banging their head against the wall. So we're here to help you get through that part. We do design surveys. We take on projects of just about any size, and there's our motto there, elegant solutions effectively applied. So let's go ahead and get started. What is a power analysis? I guess the first question you should ask is, what is power? That's, of course, statistically speaking, which it kind of always means something different than it does in the real world. The definition of power in a textbook, I found this one, is the power of an experiment that you are about to carry out quantifies the chance that you will correctly reject the null hypothesis if some alternative hypothesis is really true. And that's true. That's exactly what power is. Our stats for the masses, I try to make it a little bit more simpler, that think of power as your flashlight, and then think of significance as hiding in the corner of a room. So you need a flashlight that's powerful enough to see that significance that's really there. If you don't have enough power, you won't see significance. So you want to make sure that your power is good enough so that you're not wasting your time with your study. You know, if the significance is there and you can't see it, what good is it for you? There are two types of power analyses. There's probably more, but there's two major types. There's the a priori, which we will be looking at today, and that's performed before you do your study, and it's performed to determine the best sample size. This is the type of power analysis that's used the most. There is another type called post hoc, and that means afterwards, so it's performed after conducting a study, and it's usually done whenever you run your numbers, you run your tests, and you don't have significant findings. It's not statistically significant, and then you will run a post hoc power analysis to make sure you had enough power, because maybe those findings were non-significant because your flashlight wasn't strong enough. Significance is there, but you didn't see it. A lot of times, researchers and statisticians frown upon the use of post hoc power analyses because they are based on basically just your sample, how you pulled your sample. Everything you're using for that power analysis post hoc is it comes from your sample. So nothing's coming from theory, nothing's coming from your literature, nothing's coming from any kind of knowledge you already know. And if your sample's not good, then what good is looking at the post hoc power? Another argument is, well, you didn't have significance, so it doesn't matter if you have power or not. You know, what are you going to do, right? So, again, like I said, we will be focusing on this webinar, a priori techniques. So there's 4 things you need to determine a good sample, or to determine your a priori power. The first thing you need is this statistical significance criterion. Don't let that scare you. It's pretty much a given that we use this right here, alpha equals 0.05. And most studies set a 95% level, which if you take 1 minus 0.95, this is why you get that 0.05. And that alpha level, that's the probability we allow for type 1 error. And I'm sure in your basic statistics classes you've heard type 1 errors when you reject the null and you shouldn't have. Other words, you said you found something significant when in truth there wasn't anything significant, and that's probably the most egregious error. You don't want to make that error, so you're going to allow yourself, 5% of the time, 1 in 20 times, just by chance, I might be committing this type 1 error. I might be saying I found significance when it wasn't really there. So you allow yourself that, and that's usually the common one, is 0.05. Power we also need. A lot of people confuse power with type 2 error. They think, oh, since the statistical significance criterion is alpha, then beta is power. And beta is not power. 1 minus beta is power. Okay. The beta type 2 error is kind of the opposite of type 1 error. Instead of what you would do then is, now I'm getting myself confused because everything's done in terms of the null hypothesis. So type 1 errors, you're saying you found significance when it really wasn't. Type 2 is the other way around. You're saying you didn't find significance and there kind of was. And that's why your power is kind of related to that. Effect size, you need to know that. That's probably the big one. How large of an effect do we want to see? What that means is you might have significant findings, but what are you going to determine to be significant? I mean, do you want it to be a difference of 2 points, a difference of 10%? Do you want it to be a correlation maybe of 0.2 or more? You need to know what size of effect is really going to be significant for you. How strong of an association? How large of an effect is significant? Sample size. You need that to know your a priori power. So how large of a sample do we need to detect that size of an effect? Well, another way to look at it is use this mnemonic called BEAN, and it might help you to remember the 4 things you need. Here they are. B is beta error, the type 2 error, where power is 1 minus beta. So you remember, okay, I need a beta in there. What I need is really the 1 minus beta. E is your effect size. A is that alpha error rate, that 0.05, and N is your sample size. And as it is with many mathematical formulas, if you have 3, you can find a 4th one. So of course, what we're going to be thinking here is that I don't know the sample size. That's what I'm looking for. That's why I'm doing all of this. So I'll need this effect size, and I'll need this alpha error rate. And then I can compute this. Well, here's what we have. We have our statistical significance criterion because we're just going to use the alpha equals 0.05. Like I said, you can make it 0.01, you can make it 0.10, it's up to you, but typically it's 0.05. And we have power because usually what we'll do is we'll set our power at 0.8. 80%. That means you have 80% chance of seeing that significance that's hiding in the corner. That means 20% chance you might miss it. But as you see when we run some of these things, some of these power analyses, if you increase this power, it makes you have to increase your sample size. So it's a lot of give and take. If you would love to have a power of 99.99. However, if you feel like going out and collecting a sample of 3,000 people, go for it. Also, with your effect sizes and such, you don't want to make them so small that you might get significance with a big, huge sample and a very small effect. But really, is it really significant? If it's a difference of a point or two, is it really significant? So these are all things you need to consider as you're planning your study. How big, how much power, how big of an effect, how big of a sample can I even really get? Sometimes you just have to make the adjustments to go to that. Here's what we don't have yet. We don't have 2 things. We don't have the effect size, and we don't have the sample size, of course, because that's what we're looking for. Now, the effect size is where you can kind of get tripped up because the other 2 things were given, right? So we know alpha 0.05 and power 0.8. But the effect size is, oh my gosh, how big of an effect do I want? If you're a statistician, you're going to ask the researcher. So if I was your statistician and you're the researcher and you're conducting a study, I would come to you and say, well, if you're testing 2 different drugs, well, how big of a difference do you want to see between the experimental drug and the control group drug? Do you want to see a 10% difference? Do you want to see 20% difference? What would be significant to you? If you're a researcher, then you need to kind of know that for yourself or find it, maybe from other people that you know, other researchers, maybe a literature review. Maybe the sponsor of your study might have had this done before, or they have a certain thing they need to look at, a certain effect. So once you know that effect size, then you can use a formula which is related to the type of test you'll be using to determine what sample size you need. And this is where it gets really, really a little bit crazy. So just bear with me. We're not really going to do any computing of formulas today. However, we need to kind of know what an effect size is. In statistics, according to Wikipedia, an effect size is a measure of the strength of a phenomenon. Oh my gosh, what's a phenomenon? Well, it could be anything. Is it the mean difference? Is it the correlation? Is it percentage difference? I mean, there's different things depending on what type of test you're doing and what you're looking for. What kind of effect? First you have to determine the effect, and then you determine the effect size. So there's many ways to compute it. Here I have some down here. Here's 2 of them. A mean difference. So you're looking at a difference between 2 groups. So then you would use a t-test. Maybe you're looking at a difference of three or more groups, the means between 3 or more groups. Then you'd use your analysis of variance, right? So that's your effect. What is the difference between the means? You might want to look at an association between 2 variables. Pearson's correlation would be one. How strong is that association? Do we want a correlation that's closer to 1? Or do we think that a correlation of 0.3 might be significant? Regression's another thing to look at. How's that model? Is that model significantly different from 0 or all those coefficients? What do we want to be an effect? How big of an effect do we want a coefficient or a variable, a predictor variable, to have on the outcome? So these are things that we need to know. When you start getting into these regression ones, they're a little bit more convoluted. But as you'll see, here's some formulas. And like I said, bear with me on this, it does get better. We could use formulas. And these are based on Jacob Cohen's Power Primer. I think that's been written a couple different times. I think he started writing about power back in the 60s. I think there's a 1988 version. This is the 1992 version. Everybody who's in the psychological, social sciences, education, things like that, they usually use Cohen quite a bit in their a priori studies. But here's for the difference. So if you say you wanted a difference between two means on a t-test, then you would take your mean from one group, subtract the mean from the other group, and divide it by a pooled standard deviation. Okay, for analysis of variance, a little bit more convoluted because we have more groups, right? So we're going to take the sums of all these differences squared, and we're going to do them by the number of groups, and then you have your pooled standard deviation here. Well, actually, it's the error, the error of them, and squared, and then you take the square root of all that, so you get a nice positive number. As I said, this looks really a little bit complicated if you're not a math person. One thing I do want to point out, though, is this is why you need to get it from the researcher, or this is why you need to get the information from the literature. Because if you look at these Greek letters, when you see something Greek in statistics, that means that it is a parameter. It's something that you're guessing at, but you'll never, ever know. So this is mu, and that's actually your population mean. Well, if we knew what mu was, we wouldn't have to be figuring this out, right? If we knew what the mean of population was, and the mean of population 2 was, and the standard deviation was for them, which here's another Greek one, sigma, then we wouldn't even really be needing to be doing statistics because we just know. But statistics are guesses. So anytime you see these Greek letters, that means these are the population items that you're guessing with your statistics. So you're going to use the data, and you're going to use that to guess at these parameters. So this is why you need to be informed by a researcher or your literature. You have to have some kind of idea because you're not getting this information from your sample. This is kind of information that you're getting from previous studies or that you kind of are assuming. You might say, well, then I'm going to assume this means is this number and this other means this number. You know, you can do that, but it's not something you can do after the fact. You know, so it's not something you can do from data. So these are things you need to know up front. Same thing for here. Here's your mu's. Here's your sigma again. We have correlations. It's a little different. Now we have x's and y's, and now we're into the Latin characters. And something like this, really, you do kind of, you're not really guessing from parameters per se. It's a little bit different. However, usually when you see the x and y's, these are your observed variables usually, but not necessarily for the correlation. Correlation itself is an effect size. So that kind of, this is something that you could do after the fact or is kind of before the fact. But here, if you look at these, here, look, there's n's in there. Well, we have no idea what the sample sizes are going to be. So again, this is something that we kind of need to be guessing at. But as I said, don't worry. We're not computing any of these today. So we're going to use a statistical program that does it all for us. As I was saying before, researchers in behavioral and social sciences or who are working on their dissertations, they often rely on the Power Primer. They rely on Cohen. He actually, when he wrote this, he made use of rules of thumb that he suggested, and this is what people will use. So if they're using, say, a mean difference for a t-test, they will say a small effect is 0.2, medium effect is 0.5, large effect is 0.8. ANOVAs, they just kind of like half of these, as you see, 0.10 for small, 0.25 medium, 0.4 for large. And for your correlations, you're just going to say a small effect on a correlation is a correlation of plus or minus 0.1. Medium would be plus or minus 0.3. And a large, very strong correlation would be 0.5, plus or minus 0.5 or greater. So you don't need to use all those formulas if you want to use these for an a priori kind of thing. If you're doing a clinical trial or something like that, yes, then you should probably use the formulas a little more often. But something like this where you just, gee, I just need to have a kind of a good feel of how big of a sample I might need, you will use these. And most of the time, whenever you're using the software, you're going to go for a medium effect size. And so you'll see that. Now, what are small, medium, and large effects? Well, according to Cohen again, small is real but it's difficult to detect because it's rather small. So I would say think about maybe differences in weight between 2-year-olds and 26-month-olds. You know, maybe there's a 2-month difference there. You'll see something because they're growing, but you're not going to see a big difference. Maybe you will on some, but typically I wouldn't think you would. A medium effect, though, it's large enough to be visible to the naked eye. So you could see the differences in weights between 3-year-olds and 5-year-olds. They'd be taller even. I mean, you could see a lot of differences there. A large effect, he says, is grossly perceptible and therefore large. Let's say differences in weights between first graders and sixth graders. Very, very different. So the larger the effect, actually the larger the effect, the easier it's going to be to detect, and the smaller of a sample size you'll need. If you think about it, well, I want to see a teeny tiny effect. I want to see a real tiny difference. I need to see that difference between the 2-year-olds and the 26-month-olds. Well, you better get a big sample for that because that's a small, you need a lot of power to see that small effect. So now it's time to find the sample size. Let's use some information we have and we'll compute some sample sizes. There's a free software that you can get and you can download it from the internet. It's called G-Power. Hopefully many of you have heard about it. Maybe a lot of you have it. But you can get it. Here's the address where you can go. So what I'm going to do is I'm going to do my best here to try to close the screen out. And we are going to go into G-Power because I have it. Let's see here. Is that out? Where is it? There it is. Okay. So here's G-Power. So we'll run a couple of these and just kind of get you used to it. Now you'll see you won't need to use any formulas really. Not really. You can keep it kind of short and simple. So I have my little notes here and I'm going to try to go through them because I didn't make separate slides. I thought it might be fun maybe to try to just go through it. I'll do a quick tour. Test family, we have many different types of tests. There's exact tests, F tests, which will usually be your ANOVAs, some regressions, your t-tests, which of course are your t-tests. Here's your chi-square test, your chi-square test of independence, things like that. Your z-tests, usually that's proportions, things like that. Statistical test, if we look in the t-test family, you can kind of click over here and look at all the different ones we have. Oh my gosh, it's mind-boggling. And F-tests, here's all our ANOVAs, MANOVAs, here's some regressions. So you can pick them that way. Type of power analysis, there's your a priori. As I said, there were different types, right? I didn't even mention these ones here. Post hoc, is there an a priori's here? So you just choose the one you want. And then in here, we're going to put in our effect sizes, our alpha, our power, and any other things we might need for the test. And then we can just hit calculate. So I'm going to go ahead and start with a t-test. Okay, we'll just do a simple independent samples t-test. So I go over here and I click on t-test. And then the statistical test is going to be means, 2 independent means. Let's make it an independent samples, okay? And we have our a priori, so make sure that's checked. So I want 2 tails. Now you could have a 1-tail test or a 2-tail test. If you're not really sure of what they are, in a nutshell, a 2-tail test is saying, I have 2 groups and I want to see if there's a mean difference between them. And you're allowing either there to be an increase on one or decrease, something like that. If you're looking at a 1-tailed test, then you would say, I have 2 groups and I think group 1 is going to be greater than group 2. Or I think group 1 is going to be lower in their mean score than group 2. And it's called directional. So if you have a 1-tailed test, that's directional. If you have a 2-tailed test, that's just saying, I want to see a difference. So in this, we're just going to say, I think there's just a difference between the 2 groups. So I'll do the 2-tailed. Here's our effect size. And you can either use this to determine it, or you can just go by the convention. And here, if you just scroll over it a little bit, you can see there they are. There's your Cohen's. So we're going to say medium because for the most part, if you are working on a study, you want a medium. You're going to allow for a medium. Large is just, you know, large is, well, if you look for a large effect size, you better hope you get a large effect size because if you don't, you're not going to see anything. You're not going to see anything significant. So, and if you make it too small of an effect, you're going to need to have that huge sample. But if you make it medium, it's kind of like, you know, Goldilocks and the Three Bears. It's kind of just right. So we'll do the medium. Errors are 0.05. And now power, it always puts 0.95, which is just way, way too powerful. So we're going to put in our convention of 80, 0.80. Here's our allocation. What is this saying? This is saying that if you have the two groups, what are the sample sizes? Do we want them to be equal? So if your sample size for N, 2, which is your second group, is the same as the sample size for group 1, if you were dividing two numbers that are the same numbers, you get a 1. So that's basically what it's saying. If you're allocating equal numbers of subjects to both of the groups, that's our allocation ratio. That is 1. So then all you have to do, you have this side filled in. Just go down here to calculate, and there you go. I'm not going to worry about this too much here. There's your degrees of freedom, and here's your sample sizes. So for group 1, you need 64. And for group 2, you need 64 because it's allocated equally. So your total sample size you need is 128. So you need 128 records. And here's your power, 0.80. So you're happy because your power is 0.80 or greater. If you want to look up here at the graph, here's your critical value when you're going to say you found significance. So if you get a T-score that's higher than that, you're going to say you found significant findings. And right here is that line for it. These ones are a little confusing, but this red line here, that is if your null hypothesis was true. If there wasn't any difference between your two groups, this would be where you'd be saying it was significant. And this one here with the blue line, that is representative of all this criteria you put in, okay? And so anything that's over here, past this critical value here with the blue, that's how much power you have. So that's saying you have pretty good power there. Look how big it is. And you always want to have your blue above your red line, okay, because this is just saying that there's no difference. So you want to be able to detect that difference, okay. I like this one better, where you have the XY plot. So if you click on that, there's all this information you could put in, but if you just click draw plot over here, it kind of puts in what you already had. So what did we say? We needed a sample size of 126 or so. So what I'll do, here's our power. I like 80% power, so I'm going to go up this line. And right there, that's pretty close to 130, right? So that right there tells you how big of a sample you need. And it tells you for just about any power. Say if I wanted 90% power, then I would come up here and look, oh, I need about 170, okay? If I wanted 95% power, I'd have 210, something like that. So as you can see, with greater power, you're going to need a bigger sample size. Okay, but 80 is what we like, and that's where we're happy. Okay, and then here's a table, and it kind of tells you here's your power, and here's your total sample size, and of course it has decimals, so you always want to round up because you can't have, like, say 103.02 records. But let's go down a little bit. There it is. 0.8. So you need about 128. Okay, so yeah, there's that. Then, the protocol. It tells you just everything that you put in, and it kind of shows. There you go. Sample size, and your total, and your actual power. Okay, and you can print these up. I think just hit Control P. Well, I'm a Windows person. I don't know what you would do on a Mac. But there's that one. So let's go ahead and try another one. So that's the t-test. Let's look at ANOVAs. Okay, so I'm going to see how I can do this one. Let's say we have 3 groups. Okay, and we are wanting to compare scores, on say math scores, between 3 populations of kids. Okay. We know some things, though, from previous research. Let's say that maybe we talked to the researcher and they know some things. Okay, so we don't have to guess at it. Okay, they know that there is a standard deviation within the 3 groups is about 10. Okay, 10 points, about 10. Based on, well, actually it's not 10 points because it's a standard deviation, so it's just 10. And based on our knowledge and the populations under study, we consider a difference of 5 points between the population means to be the smallest effect of practical importance. And what that means is that, 2 points isn't going to matter. We don't care. But 5 points, the researcher says 5 points matters. So if we have a mean difference of 5 points or more, I want that. I want to be able to see that. Okay. So we want to estimate the number of cases we need to get that 80% power, and we're going to set our alpha to 0.05. Okay. Now we could go back and we could use that computation where we had the sum and the square root and the square of everything. We also could use G-power, which is very nice. So we open it. Let's go to F-test. Let's go ahead and get this out of here. See if I can clear. Oh, get it clear. So we just cleared this out. Okay, so let's go to F-test. And then we're going to look a priori still there. Now we're going to go over here and we want ANOVA. Let's do the omnibus one way. Omnibus means that what it's doing is it's going to test the 3 means to see if there's any difference in the means between the 3 groups. It's not going to tell you where they're different. So it could be that group 1 was different than group 3 but not group 2. But we're not looking at that. We're just going to look at it and say, well, is there a difference between any of the groups, any pair of groups? So we'll put that in. Here's our a priori. So here's our effect size. Then here we go with, we can determine it with the medium is 0.25. Error is 0.05. Our power 80, 0.8. And let's see how many numbers of groups. We have 3 because there's 3 sets of children, right? 3 different groups. Okay. So now what we want to do is now we know a little bit more. So we're going to determine some other things here. So we're going to hit this determine. Okay. So we know from the researcher that they told us some things. So we want to get the effect size from the means. Here's our 3 groups. And then this should say standard deviation. I can't see the S, but should say standard deviation within each group. We know that's 10 because the researcher told us 10, right? Now here's our 3 groups. So what we're going to do is we're going to kind of throw in something that'll put the 5-point difference, and then we're going to put one group in the middle that's not quite 5 points, maybe right in the middle of them. So let's say that we need to have, say we want a mean of 100, okay? And with the size of 5 there. And we're going to put this one in the middle, 102.5. We're going to make you 105. We're going to leave these all 5 here. And we're going to say they're equal. Okay. We're going to say our total sample size is 15. Okay. And it's going to calculate our effect size now, given all this information. So as we do, instead of putting in this one over here for the 0.25, let's calculate it. Here it is, 0.20. So it's a little bit less than a medium effect size according to Cohen. Okay. So let's transfer that to the main window. There it is. Now we can close this. And now we can calculate. There you go. So total sample size is 237 we would need altogether. So if we did say we wanted to go with the medium effect, so we can just go back, recalculate. See that? See how far it went down there? 159. Say we want a really small effect. Put in 0.1. Wow. So see, the effect size does make a difference. Sample size makes a difference. They all go together. I mean, say if we did a effect size again, say medium, but we wanted our power to be really, really powerful, say 90.9. Some clinical trials want a 0.9. Not so bad. We're kind of back where we were before. But if we go back to what we had computed from what the researcher knew, now we're into 300s, right? So as you can see, there's that give and take, okay? I think we might have time for another 1 or 2 if I haven't bored you to death. Let's try correlations because we talked about those. So let's go up here. And, oh, maybe we should look at the XY. Let's look at that. Let's go back here. Let's go let's say what the researcher had, 0.8, and what did they have, like 0.20, 3 groups. Okay, so let's calculate that. And let's draw our plot. Here we go. See? Just under 250. And again, you can see for all the different powers, the lower the power, the less people you need. Okay? It kind of tells you up here what you have. Okay? Good. All right, let's go ahead and clear it. Okay. All right, let's try correlation. This is under t-test. That's sometimes when you're using this, you have to go, where in the world am I going to find? And then you don't know what they call it, right? Where am I going to find it, and what are they calling it? Yeah. So for correlation, usually Pearson's correlation, it would be under t-test, and it's right here, correlation point by serial model. If you click over here, here's some regressions. Here's, these other Mann-Whitney's in here for some reason under a t-test. Basically, these are non-parametric tests that are for the t-test, but it's just kind of funny because they don't really have something that says non-parametric, but I thought maybe it might be in an exact test or something. But anyway, this is where they put the correlation. A priori, let's do our two tails again because we just want to know if there's an effect. We don't really care if it's a plus or a minus. Here's our medium effect size. Now see, it doesn't have an R, it has a rho, but we can go ahead and use that. It's rho is usually with a Spearman's correlation. However, this is how they have it in here. So there's our different effect sizes. So we'll use 0.3. There's our error. And 0.8. Calculate. See, it's easy once you do it a while. There's our total sample size. There's our power. And draw our plot. There we go. That's very nice. Okay. Now, say we wanted to see a large effect. Hardly need a sample at all there, right? Now it's gone down. Look at that. Then that's to see a large effect because you should be able to see a large effect. If it's that big of a correlation is 0.5 or greater, that's a strong correlation. 1 is the strongest. 1 is a perfect correlation. So if you're halfway there, you're doing pretty good. So you don't need a big sample. And so it's all a give or take again. Let's say if we needed a effect size, say we wanted to be able to see a really tiny correlation. Let's say we wanted to see one almost close to 0. 0 means no correlation. So let's say if we want a 0.01. How about that? I haven't done this. This will be fun. Let's see. So you need 78,483 because you really, and when you think about it, if somebody ever asks you to do that or if you ever think to do that, a correlation of 0.01 is so close to 0, you basically would need a sample size that big to see if there's anything that would be, considered. You'd have to be able to see it get that close to 0. You'd have to have something really, really big. A large sample. And that is a problem with frequentist statistics, which is what these kind of statistics are. The bigger sample you do get, if I got a sample of 100,000, well, let's put it this way. If I got a sample of 78,000, almost, or 79,000, I'd be able to see I'd be able to say something this small is significant. And really, in fact, I don't really think anybody would ever say that's significant. So, if you get a sample size that's big enough, you'll see significance all over the place because you'll have such power because of that sample size. And so, again, it's the give and take. It's the knowledge of what truly is clinically significant or what a researcher believes would be a sizable difference. That's what you want to use. I think we might have time to do a regression real quick. I know a lot of people like to do regressions, especially if you're a dissertation type person. So let's go ahead and clear this out. And we will do a regression real quick, and then we'll ask some questions. Okay, so F-test, because you use an F-test for your regression. And here we go. We are going to go to linear multiple regression. Now, for this one, what I'm going to do is we're going to call it a hierarchical regression. It's going to be a little, hopefully some of you will know what a hierarchical regression is. What you do is it's 2 steps or more, but a typical one is on the first step you're going to throw in your controls. So you'll throw in things like gender, marital status, socioeconomic status, things like that. And then on the second step, you're going to put in the things you're really interested in. Okay, so let me go ahead and start on this. And let's see here. We have linear regression. And let's see, fixed model, R-squared increase. So what this is telling me is that I'm going to throw everything in on the first step. And then I'm going to look to see how much the R-squared increases on that second step, because the R-squared is the big measure on your regression, on how much variance all those predictors are contributing to the outcome. Basically, how much error are they accounting for? Because when you draw that regression line, you have dots all over the regression line. It doesn't line up, so you have all that error because everything is away from the line. So you want to see how much of that error is accounted for. So that's what your R-squared is. So you want this to increase from the first step to the second step. So we'll go ahead and do that. Okay, a priori again. So let's go ahead and say we want to do some things here. Okay. Now I'm doing this from my notes that I wrote last night. So it's not as easy as the other ones were for me. So let's say we want a 90% chance. Say we want a 90. Okay. And say we want our alpha 0.05. And we want the R-squared change. Let's see. We do not see the R-squared change. Why am I putting it in there? Okay, so this is where we would need to do a formula. So we want an R-squared change that's large enough to add another 10% variance over what we get at the first step. So let's say that we say we're going to put in 3 controls. We'll put in gender, we'll put in marital status, and we'll put in socioeconomic status. And we're thinking that the R-squared for that model is going to be 0.3. Okay. Then what we're going to say is on the second step, we want that to go up 10%. So we want to go up to 0.4 or greater. Okay. So what we need to do is do some computations, which is in one of the many formulas. So here you would kind of need to use a formula. And then you would come up with a value. Okay. And so what we were going to do then is put the type of a power analysis we have here. We have your input parameters. We have our F-squared here. If we did that where you had the 30 at the first step and then a 10 increase at the second, we're going to have like 1.667, something like that. So it's very, very close to the 0.15. Okay, so we have our power. We have this. Okay, we have 3 that are going, 5 altogether that are going in, right? 2 we're testing. So we're throwing in 3 at the beginning on the first step. And then on the second step, we're going to test 2 of the things we're really interested in. Maybe it's some kind of measure for emotional intelligence and something for self-efficacy. Maybe there's 2 different measurements there. And the outcome is going to be maybe, I don't know, job satisfaction, right? So we're going to put in gender, socioeconomic status, marital status on the first step. Then on the second step, we're going to put in our 2 tested predictors, which will be our self-efficacy and our emotional intelligence. So total, all our predictors, the 3 plus a 2 are 5. Okay, so there. Let's calculate it. Close that out of there. Oh, that's not bad. You only need 80. That's not so bad. And there's your actual power. Okay, so that's pretty good, actually. A rule of thumb for regression is you need 10 records for each predictor. Some people say 20 records for each predictor. So if you're going with the 20 for each, yeah, this is a little low, but this is what G-Power is saying. So let's look at the little plot. And there we are. Let's see if you wanted to go up here. Oh, there we are, because we're at the 90 now, right? 90% power. So there's our sample size. Okay. So at 80% power, you could have somewhere between 60 and 65 people, and you'd be just fine. Okay. So I think that's about it. Let me go back to my slides and make sure I didn't miss anything. We found some sample sizes, and I hope your eyes aren't totally glazed over, but it's something to play with. There are some other, that's just G-Power. SAS has code. R has code. In fact, I think I will put some up on the board. I just didn't get to it yet on our blog. Within the next week, I think I will post some code for SAS and R and such, so you can maybe play with that. But here's some references. UCLA, they're just great. Their Institute for Research and Education is just a great site. I mean, annotated output on all your analyses in SPSS, Stata, SAS, R. I mean, it's just great. So here's something for power, and they walk you through a few of them, which are very nice. StatSoft site has something on how to perform your power analysis using Statistica software. And there's theirs. This is great. I don't know why it's called Mormons in Science, but it's not quite complete. But like I was doing the walkthrough, he walks you step by step through it for all the different types of tests. I think even a Mancova's in there because they can get very complicated. And then there are times you're going to be doing some kind of power analysis for a type of study where it's just not going to be simple. Then you need something like PASS software or even SAS, something like that where maybe you have a Mancova or something like that where it's a little bit more involved. And it's just not that easy. But hopefully you try to keep, parsimony is our friend. Keep it as simple as possible. Don't make it more convoluted than you need to. And that just comes with practice and the literature. See what's out there. See what's been done. Tweak it a little. You don't have to reinvent the wheel. Here's something I found too. And in fact, I quoted it. I quoted it as the textbook definition of power. And so here is his article. I thought I'd at least give him that credit. And, maybe you can take a look at that, and I think it'll be useful. And check out the blog. Here's the link to the blog. I don't have much on it now, just newsletters and such. I need to start maintaining that more. So probably in the next week I will put some SAS and R code up there. And maybe some other things as I find them. I just like to be able to share more on that. So that's good. Thank you for attending. Here's all my information. There's a phone number if you ever want to call us. Shoot me an email. I just love talking about stats. I like hearing where you're at. Simple questions. Sometimes I'll have a very convoluted answer for you. Sometimes I might have a simple answer, and a lot of times I'll say that depends, because a lot of things about statistics, that's my big answer. Well, it depends. Just like power analysis, it depends. What's your effect size? It depends. What's your test? So we have some time for questions and answers, and I'm going to bring Heather on and see if she has any questions that you've asked, and I'll do my best to answer them. So let me see. Are you there, Heather?
I am here.
Yay. Do you have any questions?
Hear me? Yay. I have just one comment that came through. Pavlova, I believe I'm saying it correctly.
Hi, Pavlova. I know Pavlova.
Yes. Okay. Well, there you go. She said that I thought power was a function of the variability of the data. Is this correct?
It is. If you look at it, you can look at it that way. It is, because if you looked back at the measures, let's see if I can make this go back. If we look back at these formulas, this is like your standard deviation formula, right? And this right here, actually, right here is variance. Okay, so it is related to that. It is a function of that. It's actually standardized. You'll standardize it for your effect, and it is a function of the variance. They actually are. So she's right. She's right. That's just it's a little bit more detailed way of explaining it, and so I'm trying to keep it simple. But Pavlova, you're right. It does. It has quite a bit to do with variance. I guess what I could say as far as that goes for everybody is that you get significance, right? So you'll get your study done and you go, ooh, I have significance. Ooh, I have a p-value less than 0.05. Yay. Well, okay, it's significant. It's a difference. Say you had a mean difference, say with this, right? So say you had a mean difference and it was significant. Okay, good. How significant? You can't use the p-value to say how significant it is. It either is or not. You're not allowed to say, oh, I got a p-value of 0.0001. That means it's really significant. You just don't do that. It either is or it isn't by that 0.05 if that's what you're setting. However, the effect size tells you the magnitude of the difference. So that's where it gets standardized. So your means for all your groups, you have to kind of be on the same kind of metric for that comparison of the magnitude. And so you say, okay, I have my statistical significance. But how big is that? How big is it? And that's where you have those measures, about what's a small, medium, and large effect. So if I had, say, that the t-test, and standardized is the effect size. So, oh yeah, I had a significant finding. Well, if they're bigger than this, say if I have an effect size of 1.5 or something like that when I did the computation, I could say the magnitude is very large between the two groups. And that takes into account your variability, because what you have to do is you have to adjust that variance, because maybe your variances aren't the same in all your groups. So you kind of have to adjust that so you're comparing apples to apples, more or less. But yeah, so your significance tells you, yes, it's significant. But the effect size tells you how big, how much. So that's about all I have to say about that.
Okay. Well, Pavlova also said that the software doesn't ask you for the variability, right? When you
It does. You can go into it and do the variability. Let's see if I can pull it back up here. Kind of whenever we were going into the F tests, and let's see, the one-way ANOVA, right here, where you're doing the input parameters. Remember we went through that? We were looking for the effect size from means. Here you can do effect size from variance, okay? And you can put in information you want there, okay? So it does allow you to do it, and a lot of programs do. Yeah, I'm not going to really show it today, but Pavlova, you can play with it, and see how it'll work for you. And look, Google it. You can Google a lot of things, and if many of them are saying the same thing, you're probably a good probability that it's correct. But there are some resources on the G-Power, and you can look and see how to maybe to compute from the variance. But you can do it either way.
And we have another question from Tony.
Okay.
He's asking about logistic regression.
Okay.
He wasn't able to see your G-Power window, but I don't know if he's able to see that now.
Gosh.
Yeah.
I hope other people were able to see it.
He's asking if he knows the sample size. If they're different, you have a sample size of 20,000 and you have a sample size of 500. How does it affect your power analysis and the effect size?
Something that big, it shouldn't affect it too much. But in any case, you want to try to get your sample size as big as possible. I mean, not as big as possible, as equal as possible, right? But a logistic regression, is he talking about like the outcomes, the dependent variable, as far as the yes and no's?
He's just asking him, yes. He said
okay.
yes.
Okay. The problem you have to worry about there is something called separation or quasi-complete separation. I don't know if you've heard of that before, but sometimes if you don't have so many, say you have all yeses and not many nos, then you might have a lot of things load up on the nos and nothing on the yeses, and then you're going to get something called separation. And that's something you don't like, because you get huge inflated standard errors, and it's just ugly looking. So if you're doing a logistic regression, yeah, you might want to try to make it up front. If you're using a convenience sample, maybe try to get ones that are yeses and nos, get them kind of even. You don't want to cherry pick, and you don't want to go on a fishing expedition. But sometimes with using certain inclusion and exclusion criteria, you can get them equal. If you don't, yes, it does affect power sometimes if you have many in one group and not so many in the other, because you just can't see the differences. Well, it's like it's overpowering on one versus the other. But really with a logistic regression, something like that on the outcome is separation is the big thing we don't like. And then you also have your other types of sensitivity. You can use that sometimes for those types of logistic regressions and such. It's a different one we didn't cover today.
And Tony thanks you, Elaine. He understands it.
Yay, I'm glad. Thank you, Tony.
And I have another question. This is from Frank. He said in SPSS it gives you the p-value for a particular test, whichever one you're using. Should a p-value equal to 0.01, should you just report it as less than 0.05?
It depends on what it depends on what you're writing for. It depends on your journal article, the journal you're writing for, the university you're writing your dissertation for, the sponsor you're writing your study for. I always like to report the actual p-value. Of course, you'll see in many journal articles, they will just report less than 0.05. Or less than 0.01, or whatever they're setting as their level of significance. You could do it either way, and I myself like to report the actual p-value and also give that effect size after, because you can always compute the effect size you know, after you get your significance. In fact, SPSS prints that out in many tests. They'll give you the actual power, especially on the ANOVAs. You can ask for it.
Okay. Frank was also asking if you could discuss the value of a power analysis when your sample is actually the population.
I don't know how much value there would be, because if your sample is actually the population, you're going to be doing a census. So you're basically going to be looking at everything anyway. So then you basically, that's it. It is what, you're not guessing at anything. So you're not trying to look for any kind of effect. You're just going to take all the information and look at it. So I don't know how useful it would really be. It would be, maybe then that might be something where you could actually run it like a post hoc and say, this is how big of a sample I have. I mean, because if you know how much of everything you have, you can look and see what the achieved power was. I don't know if you needed a priori to, you know, you could, I guess, you know what, if you had a small population, I'm thinking in terms of huge populations, right? But if you had a small population, you could still do an a priori analysis. Just do it maybe backwards, you know, instead of doing the a priori, use the post hoc, put in your total sample size here, right, and then put in the things just to make sure you have enough. So if I was to do it the other way around, say I was doing the ANOVA, and I did it post hoc, and the effect size, say I want to say, okay, to get a medium effect, do I have enough? There's my error. Say I have, okay, and I have a population of 250 people, and they're broken up into 3 groups. Okay, so I can calculate it. Oop. Okay, so all right, so it doesn't like that. So let's say I have 300. Okay, so this is assuming right away, right there. That tells you they want to assume equal sample sizes. All right, so there you go. Boy, with that big a number, see, I'm going to be very, very good on my power, 0.97. And you can play with it. You can put in different numbers. You know, you can put in 3. Oh, now it needs to be greater than 3. Let's say if I have 6. Oh, look at my power. I can't see anything there because my sample size is so small. So see, you can work it both ways, which it's kind of fun to play with, actually. And it's actually fun to play with until you get a good grasp in your own head. Okay, large effect means small samples. Small effect means large samples. And you can do that. You can play with this and see how that works.
Okay. We have another question from Tony.
We got time for about one more. Yeah.
Okay. We got one more, actually.
Okay.
Yes. On the G-Power software, he wanted to know if you can use it for logistic regression as far as the test is concerned. You
mean the a priori, or to run the actual analyses?
I believe the actual analyses is what he's asking.
No, this just figures power. It doesn't run statistical tests.
So it's just, okay, just the power. Okay.
Just for power, yeah.
Okay.
So if there's any other questions, I guess there's not, Heather said, but email me, you know, and I can always put it up on the blog and, you know, give you guys answers. But I think that's about all we have for now. But I want to thank everybody for coming, and I really do hope that you did get something out of this. I know power analysis, it's tricky, it can be a little convoluted. I have researchers calling me all the time, I need a power analysis, and I don't know how to do it, you know. But once you get the hang of it, once you understand what you're doing and why, and you play with it a little bit, it's actually kind of fun. And if you're going to be pursuing research, it's always nice to be able to do your own power, because you don't want to start a study unless you're sure you're going to be able to, you know, have a big enough sample to find what you're looking for. So, but thank you everybody for coming, and thank you, Heather.
Yes, thank you.
And I will send out some information soon so that everybody can download this and listen to it all you want. But have a great holiday too, and then we'll see everybody again, if we don't talk to you sooner, in January.
And we'll be sending out the recording and everything, so you guys will have it as well, okay?
Exactly, like Heather said, yes. Okay, well, thank you guys. And thank you, everybody.
Guys.
Bye-bye.